Assalamu alaikum dear students. In our today's lecture, the following topics will be covered. It includes pressure volume work, then we will derive some of the mathematical forms of isothermal reversible expansion and isothermal irreversible expansion, and we will discuss maximum work done in a reversible expansion. Then we define what is internal energy, also the symbolic representation of internal energy and sign convention, and finally we will discuss first law of thermodynamics and its various forms. First of all, we need to discuss what is pressure volume work. Pressure volume work in thermodynamics is very important as we considering the gas expansion or compression, as the pressure is the force per unit area on the piston. That is basically this pressure is an external pressure that is applied externally on the piston to compress a given volume of a gas. So in thermodynamics, when we talk about work done, we talk about pressure volume work. This is very important. When we talk about thermodynamics, we talk about PV work. It is important to remember this is the driving factor, that this is the external pressure, P external, that is the driving factor for evaluating the work done in thermodynamics. So this is a diagrammatical representation of pressure work. Consider a gas cylinder. This gas is enclosed in a certain cylinder with the help of a movable and frictionless piston. This gas has a constant pressure, and this, as you know, the gas exerts a pressure on the walls of the piston, and this pressure equalizes by the external pressure applied from the outside or applied from the surrounding. As this external pressure exerts a force on the piston, so if this external pressure decreases, then this piston slightly moves up through a distance L up to this point. So what happened, how we can calculate this pressure volume work by using this formula, as work equals to force multiplied by distance, as force is represented by small f and distance here is small l. As you know that the pressure is the force per unit area, from this expression we can derive force, that is external pressure multiplied by area. Applying the value of force in the above equation, then we will get the value of work done, that is work equals to P external multiplied by del V. We can replace this area into length with del V, as del V is the increase in volume. As the system is doing work on the surrounding, so it bears a negative sign. Yesterday I taught you about the convention of work, when we use the negative sign and when we use the positive sign. As the system is doing work on the surrounding, this is the work done by the system, so the value of work is negative here. So we replace this positive sign from this equation to here in negative sign, as the system is doing work, as the gas is expanding. In our previous slide, you see the gas is expanding. This system is doing work on the surrounding, as the piston is moved from this point to this point. So the gas in the system is doing work on the surrounding. So this work done is negative, and we got the product of pressure and change in volume. This is our final work expression. So sorry, I have a little cough. So this is our little conclusions we derive from the above mathematical expression. If the work done is done by the surrounding on the system, then the work done can be represented with the positive sign. This is the opposite case as I taught earlier. If pressure volume work can be expressed as a product of pressure and volume, so its units must be in liters and atmosphere. The work done by the system is not a state function. Why it is not a state function? Because the work done does not depend upon the initial and final state of the system. Now we need to discuss some of the problems related to pressure volume work. This is the question: calculate the pressure volume work done when a system containing a gas expands from 1 liter to 2 liter against a constant external pressure of 10 atmosphere. Express the answer in calories and joule. As we know that this relationship, as we derived earlier, that is work done equals to uh, P external into V2 minus V1. As this is the work done by the system, so we use negative sign here. So putting the given values in this formula, and we got the work done in liters into ATM unit. Finally, we need to convert these liter into ATM into calories and joule. We need to multiply with this factor and divide this factor. When we do so, liter ATMs cancel out with liter ATMs, and we have left with calories. That is minus 242 calories, as 1 calorie equals to 4.184 joule. So you need to multiply your answer, that is 242, with 4.184, and you will get your answer in joule as well. So in this numerical problem, we calculated the work done in calories, and we have calculated the work done in joules. Now comes to our another topic, that is isothermal reversible expansion work of an ideal gas. Consider an ideal gas enclosed in a cylinder with a movable and frictionless piston. The pressure inside the gas is P, while the external pressure is P external. If the external pressure of the gas is decreased by an amount dP, then the external pressure is also decreases to P external minus dP. So when the external pressure decreases, this piston moves upward to this point, for example this point, to a small distance dl. So we can calculate the small work done up to this point by using this formula: dw equals to p multiplied by a into dl, where you know that a multiplied by dl can be replaced with dv. What is dv? dv is the change or increase in volume. We need to integrate this expression in applying the integral operator on both sides of the equation. What happened? The integral operator here, we have dw, this d is cancelled with the integral operator, and we have left with w on the left hand side of the equation, and we have the limits of v1 and v2. This is the limit integral. As you know that by using an ideal gas equation, the value of pressure is P equals to nRT over V. Putting the value of pressure in the equation number 1, then we have W equals to minus limit integral of V1 to V2, nRT over V into dV. As you know that all the constants should be placed outside the integral. So here small n, ideal gas constant, or T is also constant over here, as the operation is isothermal. So putting nRT outside the integral, and we have left inside the integral as dV over V. Apply the integration operation, and we got the final work done, that is W equals to minus nRT into log natural V2 over V1. Since we know that P1 V1 equals to P2 V2, so by cross multiplication and dividing these variables, we got V2 over V1 equals to P1 over P2. Putting the values of V2 over V1 in this above equation, we got work done in terms of pressure, initial pressure and final pressure. We can also convert this natural log into common log by multiplying it with 2.303. So the final expression is final expression of work done in case of reversible expansion is minus 2.303 into nRT log of P1 over P2. Similarly, we can also calculate the work done for irreversible expansion. For that, we have We apply the same integration operator inside the pressure volume work, as this external pressure is dependent upon P2. So this external pressure has been replaced with P2 by applying the integration on this change in volume. In the increase of volume, we have left with V2 minus V1, as these are the limits. So we have the change in volume is replaced with these limit variables. So we have left with our work done, that is P2 into dV. This is the work done expression in case of irreversible expansion of an ideal gas. So these are the problems of reversible and irreversible expansion of a gas. The question of this problem is 1 mole of an ideal gas at 25 degrees Celsius is about to expand reversibly at constant temperature from a volume of 10 liter to 20 liter. Calculate the work done by a gas in joules and calories. We need to calculate the work done in calories and joules. First of all, we have to apply the formula that was derived earlier. In case of reversible expansion of an ideal gas, we have minus nRT into log natural of V2 over V1. We can also change this relationship with the common log by multiplying with the expression of 2.303. Applying the formula, putting the values of constants, putting R is constant, as you know, this is an ideal gas constant, and the value of R is 8.314. Temperature is 25 degrees Celsius. You need to convert this temperature into Kelvin. How can you convert temperature into Kelvin? By adding 25 into 273. Then your answer of temperature is 298. What is V2? V2 is 20 liters and V1 is 10 liters. Just putting the values and you got your answer in joules. You also need to convert your answer into calories. For that, you need to multiply it with 1.987 and divide it with 8.314 joule. With this factor, you need to multiply and divide. Then you can easily convert your answer in joules with your answer in calories, as joule cancel out with joule, and your final results ultimately came into calories. So in here, by applying this formula, you can easily convert your work done in joule as well as calories by using these relationships. This is your problem 2. Here you need to calculate the work done when 1 mole of a gas is expanded reversibly and isothermally from 5 atmospheres to 1 atmosphere at 25 degrees Celsius. Again, here it is a reversible expansion, so we can apply the formula of work done in case of reversible expansion, that is W equals to minus nRT log natural. Ln is log natural P1 over P2. You can also change this log natural with common log by multiplying it with 2.303. Here P1 is 5, however P2 is 1. Applying the values of constant as well as in the given values, we can easily calculate the work done, that is minus 3988 joules. If you wish to convert the value of joule into kilojoule, then you need to divide 3988 with 1000, and your answer will also be calculated in kilojoule, that is minus 3.988 kilojoule. And now this is our another topic, that is internal energy. First of all, we need to define what is internal energy. It is the total of all possible kind of energies of a system. In a system is dependent on the thermodynamic properties, as we discussed earlier. What are the thermodynamic properties? Temperature, pressure, volume. So internal energy of a system is a state function, as it depends upon the initial and final state of the system. Moreover, internal energy is an extensive property, as it depends upon the amount of the matter and size of the system. As I already told you in my physical class, that what are extensive and intensive properties. So internal energy, please keep this thing, remember that internal energy is a state function, and internal energy is an extensive property as it depends upon the amount of matter contained in a system. So, this is all about internal energy. Now we come about to symbolic representation of internal energy. Internal energy is represented by a symbol E. In some books, some authors use symbol U for internal energy. In thermodynamics, we are concerned with the initial and final state. For example, if we need to calculate the change in energy, then the change in energy can be calculated with the difference of final energy and the difference of initial energy, that is delta E equals to EF minus EIN. Delta E is positive if the value of EF is greater than initial energy. If delta E is negative if the value of EF, that is final energy, is less than EIN. So, a system may transfer energy to or from the surrounding as heat or work or both. Units of internal energy, usually and most commonly we use SI units of internal energy, that is joules. Moreover, internal energy can also be expressed in calories. You also know this famous relationship, that is 1 calorie is equals to 4.184 joule. Please do remember this relationship, as usually we use this relationship in order to convert your answer from calories to joule, or joules from calories. So this interconversion, for this interconversion of joule to calories or calories to joule, you must remember this type of relationship. First law of thermodynamics. So this is the last topic of our today's lecture. The first law of thermodynamics is basically a broad principle of law of conservation of energy. It states that the total energy of an isolated system remains constant, though it may change from one state to another. When a system changes from one state to another state, the total energy of the system is constant according to first law of thermodynamics. So, after statement, we need to derive the mathematical form of first law. When a system changes from state A to state B, suppose your system is changing from state A to state B, then its energy of state A must be EA and energy of state B must be EB. B is your final state and A is your initial state. So change in energy is expressed as delta E equals to EB minus EA. The energy change is brought about the evolution or absorption of heat. As heat is the deriving factor, it may absorb inside the system or it may evolve outside the system. Or second deriving factor here is the work done. Work done by the gas on the surrounding in order to expand it. We can write the above equation. This equation by changes the value of final energies to Q and initial energy of the system to W. That is the final form of first law of thermodynamics is delta E equals to Q minus W. This relationship is known as the mathematical form of first law of thermodynamics, where Q is the heat supplied to the system and W is the work done by the system. So from this first law, we can also conclude a final statement that is the net energy change of a closed system is equal to the heat transfer to the system minus the work done by the system. So this statement is derived from the final mathematical form of first law. Other definitions of first law are also given below. First law may be defined as whenever energy of a particular type disappears, equivalent amount of energy must be produced in order to balance the system. Moreover, the total energy of the system and surrounding remains constant whenever the system or surrounding moves from the initial state to final state. And the third definition is it is impossible to construct a perpetual motion machine that can produce work without spending energy on it. So, the this energy is very important in case of first law of thermodynamics, and it must be conserved when a system changes from one state to another. Now we will discuss some of the special forms of first law of thermodynamics. As we know that the mathematical form of first law is delta E equals to Q minus W. This is the mathematical form of first law of thermodynamics. For various thermodynamic processes, we need to derive the first law of thermodynamics. For case 1, we talk about cyclic process. Yesterday I told you about the cyclic process, that for cyclic process change in energy is always zero. So putting the value of delta E in the first law of thermodynamic expression, we got the final expression for cyclic process, that is Q equals to W. Now case 2 for an isochoric process. As you know that for isochoric process there will be no change in volume. When there is no change in volume, then there will be no work done. As you know, in thermodynamics is the product of pressure volume work. When volume is zero, your work done must be zero. So replacing W equals to zero in this mathematical form, for an isochoric process, your change in energy equals to heat absorbed or evolved by the system at a constant volume. In case 3, for an adiabatic process, you know that there is no change in heat gain or lost. So for adiabatic process, yesterday I told you that dq equals to 0 or q equals to 0, there is no heat change. So putting the value of q in this mathematical form of first law, then you see that after putting the value q equals to 0 over here, we have left with delta E equals to minus W. So the change in energy is the work done by the system on the surrounding. So this is the final energy in case of adiabatic process. In case of isobaric process, the pressure is constant, so work done is P del V. So replacing the value of work in equation number above equation of first law, so the change in energy is equals to delta E equals to Q minus P del V. So these are all the various forms of first law of thermodynamics in case of cyclic, in case of isochoric, adiabatic and isobaric process. So you need to evaluate all these values by using these relationships. So here are some problems about first law of thermodynamics. In this problem, you need to calculate del E, Q and W if 2 moles of hydrogen at 3 atmosphere pressures expand isothermally at 50 degrees Celsius and reversibly to a pressure of 1 atmosphere. In isothermal, as the gas is isothermal expansion, so the gas is ideal, so the value of delta E is equal to 0. Putting first law of thermodynamics, that is delta E equals to Q minus W. Here delta E is equal to 0, so Q equals to W for that relationship. For a reversible process, you know, the work done is can be calculated by using this formula, applying the values of all putting all given values and constant values inside this formula. The work done is easily calculated, and in calories, your work done is 1410 calories. As you know, from the above expression, your heat is equal to your work done. So in that case, your work done is equals to your Q. So the value of Q is also the same. So you have calculated the value of work, you have calculated the value of heat. Here comes another problem. A gas enclosed in a cylinder fitted with a frictionless piston expand against a constant external pressure from 1 atmosphere from a volume of 5 liters to a volume of 10 liters. In doing so, it absorbs 400 joule thermal energy from its surrounding. Determine delta E for that process. Here in this numerical problem, the value of pressure is given, the value of initial and final volumes are given, the value of Q is given. You need to calculate the change in energy. Applying first law of thermodynamics, this is the mathematical form of first law of thermodynamics. The value of Q is given, however we need to calculate the work done. Putting the work done expression over here, the formula of work done as the pressure is 1 atmosphere, V2 is 10 and V1 is 5. Just calculate this value and your work done comes out to be minus 5 liter into ATM. You need to convert this unit into joule. For that we will use this expression 1 liter into ATM equals to 101.2 joule. So you need to multiply 5 with 101.2 joule and your answer will be minus 506 joule. Substituting the values in of work done in equation number in equation number 1. Your change in energy is equals to 400 joule, that is your heat, already a given value, and minus 506 joule, that is your calculated value of work. Finally, you got your change in energy in joules, that is 906 joule. In this numerical problem, you easily calculate the change in energy by using the first law of thermodynamics. So students, this is all about today's lecture. If you have any questions, you may ask directly from me, you may email me, or you may add up your question in our university portal. I thank you all for your attention. Please feel free to ask if you have any question. Thank you.